We're in the middle of a unit called Momentum, Work, and Energy, and we've finished the momentum part, so we're moving on to the middle section, Work. Now our goal is to get all the way to the conservation of energy. The thing that ties this whole unit together is the concept of conservation. So we ended our previous talk on momentum with the conservation of momentum in 2 dimensions. Okay, the idea that whatever momentum there was in a system before an event or before a collision is equal to the momentum in the event or in the system after the collision or after the event. We're going to see the same idea happening with energy, but before we get there, we first have to talk about a concept called work. Now, work is a bit of an odd concept. It's another one of those science words that has a word in common with normal English that doesn't at all mean the same thing. So when you work, normally, you're putting some effort into something. Okay, but the definition of work in physics is a little bit different. And I'm going to try and illustrate it with a creation of my daughter's. So this, I think at some point, at first, was a house. Now it's a jail, she tells me. I don't know for who. I just want to allow you to appreciate the magnificence of this creation, though. So you can see the jail door over here. It has a nice set of stairs leading up to it. I don't know what these things up at the top are, but she tells me that this white thing sticking out the side here, this is the hammock. That's where the adults sleep. I don't know what that means. But we're going to use this house to kind of illustrate what work is and what it is not. So if you were, this is Sally. If Sally was to push on this jail with all the force she could muster, she's not going to be able to move it. She's not going to be able to cause a displacement, even though she's maybe exerting a lot of force. She feels like she's working hard, but she's actually not doing any work on this jail. Okay? In order for it to be work, she has to have caused the displacement of some kind. So just pushing on an immovable object is not doing work. Okay? But if she would sneak up on Jessie, or whatever, from this hammock she's been sleeping in, it's a very fragile hammock. I don't know how it's supposed to hold people, but whatever. She sneaks up on Jessie. She's going to exert a force on Jessie, causing a displacement. That was work that was just done. So you can think of any number of examples of actually doing work. Pick any sport that you can play. If you're throwing a ball, you're doing work. If you're hitting a golf ball, you're doing work. If you are throwing a javelin, whatever, you can think of almost anything, and that'll be an example of work being done. But anytime that a force is exerted without a change in position, without a displacement, then you do not have any work being done. So work is the result of force acting on an object to cause a displacement. Displacement. Okay. Another important way of thinking about it is as a transfer of energy. So when Sally was pushing on the jail, she wasn't changing the energy of the jail at all. She was exerting force on it, but the jail wasn't changing in any way. But when Sally pushed Jessie off the ledge of the jail, then suddenly Jessie was moving forward. She had different energy than she had when she was just standing there. Okay, so work is a force that causes a displacement, but it's also a transfer of energy. Okay, and we gave the example of a whole bunch of sports objects moving. Those can all be said that they had work done on them. So a golfer using a club, the club swings and hits the ball, and the ball has a force acting on it, which then causes a displacement of that ball in whatever direction the club is swinging in. If you're any good at golf, hopefully. Okay, so then we would say that the club did work on the ball. Force caused the displacement. So then we have a formula for this. work is just a nice W. Isn't that a nice change? It's not P as momentum or something like that. It's just W as work. Work equals force times displacement. Okay, and in some places you're going to see displacement as change in x, change in position instead of change in d, but we've been doing change in d, so we'll leave it that way. Okay, both of these things are vectors, but work is not a vector. Work is a scalar. You are either adding energy to something or subtracting energy from something. You are not doing work in a certain direction. Okay, so work is not a vector. So we're just going to label these things. This is work. This is force. And this guy over here is displacement. Okay, units are important. Force is measured in newtons. Displacement is measured in meters. And so then work is measured in newtons times meters. Hopefully that makes sense from the formula. Newtons times meters. So then this is Newton meters. Work is measured in Newton meters. But Newton meters has a name for it. Okay, so just like kilogram meters per second squared, force, has been named newtons, Newton meters, or the units of work, have also been named joules. Okay, so work is force times displacement, which is measured in Newton meters. Totally fine, you can measure it in Newton meters, but usually that's going to be measured in joules. Now this is important. Remember, the force that we're putting into that equation is the one that is causing the displacement. Okay, so you can't be putting gravity into that force spot when something is being pushed sideways. So when the displacement is sideways, gravity can't be the force that's causing that displacement. Gravity's not doing that work. Okay, it's important that the force and the displacement, that the directions match. So let's do an example here. A box with a mass of 10 kilograms falls straight down a distance of 2 meters. How much work is done by gravity? So gravity is exerting a force and causing a displacement. Okay, and so work, let me just get the right color pen. Work is force times displacement. And in our case, the force that we're talking about is the force of gravity. Okay, now the question doesn't tell us how much the force of gravity is, but we know it's mass times 9.8. So work equals mass times g times displacement. 10 kilograms times 9.8 meters per second squared times 2 meters. Okay, that will give us the amount of work that was done by gravity on this box. It also tells us how much additional energy was added to the box. Okay, remember that work is also a change in energy. Now, it's a little bit more complicated than that with gravity because the thing is also changing height. So then there's a potential energy change and a kinetic energy change. So don't worry about that too much right now. The amount of work that was done was 98 times 2, which is 196 Newton meters, or 196 joules. And I am going to put a plus sign on there, not because it has polarity or anything, but because we are adding 196 Newton meters or 196 joules of energy onto something. Okay, so it's a positive transfer of energy. Energy isn't being subtracted from the thing, from the box, it's being added to the box. Example 2. A child pulls a rope attached to a toy with 10 newtons of force, but 20 degrees above the horizontal. The toy moves 6 meters. So it tells us that the toy's displacement is going to be 6 meters. We're going to assume that that's horizontally. This toy is probably not going to float into the air. Right? That doesn't generally happen when you're pulling on a rope. So this is the situation that we have. Our toy is being pulled with 10 newtons of force, somewhat upward like this, but also mostly horizontally. So we said that the force that needs to be put into that work formula to calculate the amount of work has to be the same direction as the displacement. And since we're assuming that the displacement is horizontal, we have to use the horizontal component of this 10 Newton force. Okay, so here's the horizontal component. This is the vertical component, but we're not going to use the vertical component in this thing. We're going to call this Fx, the x component of the pulling force. Okay, so we're going to do work equals force times displacement, but the force that we're going to use is that Fx there. So you can just put the Fx straight into the formula if you want to. I'm going to start by calculating it separately. So Fx is 10 newtons times the cosine of 20 degrees. You can put that in brackets if you want. Doesn't really matter. 10 newtons times the cosine of 20 degrees. And that's 9.4 newtons. So it's not 10 newtons that's causing a displacement on this toy. It's 9.4 newtons. It's just the horizontal component. Okay, and so now we can do the work equals force, I'm going to call it the x force, times the displacement. .4 newtons was the work that was done in the correct direction, times 6 meters is the displacement that the toy went through. Okay, and so that together is 56.4 Newton meters, or 56.4 joules. 56.4 joules. We're going to get used to writing joules most of the time because we're going to roll this right into energy afterwards, and energy is generally measured in joules. Okay, this is also an addition of energy, 56.4 joules. Now B, if the toy is moving at a constant velocity, how much work is done by friction? Now we can do this a couple different ways. First of all, we can think about this. If this object is moving at a constant velocity, that means all the forces acting on it should be balanced. Okay, and so then if we were to look at the work equals force times displacement formula, so first of all, constant velocity means acceleration equals 0, which also means that net force equals 0. Okay, and so if we're looking at it that way, work equals net force times displacement. The net force acting on this object, if it is going at a constant velocity, is 0. And so that means that the total work that's being done on this object is also going to be 0. Okay, so net force is 0 newtons because it's constant velocity. The displacement is still 6 meters. And so that means that the total work being done on this object is 0 joules. So no energy is being added or subtracted from it in total. Okay, but we know that the pulling force, Fx, is doing 56.4 joules of work on that object. And so if 56.4 joules is being added to it, 56.4 joules must be being subtracted from it by friction as well. Okay, and so we can know right away that the force of friction is going to be doing negative 56.4 joules of work on the object. But I want to do this one other way. So because F net is equal to 0, and F net in this case is the Fx we were talking about, and the force of friction then we know that the force of friction is the negative version of Fx. Okay, so force of friction and Fx, they're equal, but they're in opposite directions. And so then if we were to do work equals force times displacement, force of friction times displacement, then the force of friction that we put in there is negative 9.4 newtons, okay? Because if you look up there, Fx is 9.4 newtons in the forward direction, so it's negative 9.4 newtons times 6 meters. And so the work being done by friction is equal to negative 56.4 joules. So all the energy that was added by the child pulling the toy is subtracted by friction pulling it backwards. And finally, how much work is done by gravity? So we said a little bit earlier that the displacement and the force must be in the same plane, must be in the same dimension. Okay, and so gravity is pulling downward, the displacement is happening in this direction, and so gravity just isn't involved in that work at all. And so we can do work equals force times displacement, but let's just throw gravity in here. Okay, work is the force of gravity times displacement, but this displacement must be in the y direction. Okay, gravity is a y force, displacement then needs to be in the y direction, and there is no y displacement. Okay, and so the force of gravity, no matter what it is, doesn't really matter because the y displacement is 0 meters. And so the work done by gravity is 0 joules. Nothing is happening in the y direction, so 0 joules. Now the last thing that we're going to look at is force position graphs. So work can be calculated using these types of graphs by finding the area under the curve. Okay, or the area under the graph, however you want to see it. We're not going to do very much with these, but it's going to be useful a little bit later just for some deriving work. Okay, so if you look at this force position graph down here, I've already split it up into these two pieces. And if we figure out the area under this portion of the graph and then under this portion of the graph, we should be able to calculate the work done. Okay, so let's think about this for a second. The force exerted in this section is 4 newtons, but not for the whole time. It just peaks at 4 newtons. It started at 0 and ramped up to 4. So the average for this section is going to be 2 newtons. Okay, and the position change is 2 meters. So we've got the force times the position change, or times the displacement, gives you the area under that part of the curve, which gives you the work. Okay, and so this is part number 1, and this is part number 2. Okay, since there's a different rate of work being done for both of those things, we're going to do them separately. So the work for section number 1 is going to be 4 newtons divided by 2 times 2 meters. Okay, now I haven't written this in an area type of way. That shape is a triangle, right? And so the formula for the area of a triangle is the base times the height divided by 2. But what we've done here is exactly that. This is the base times the height divided by 2. So this is the area of a triangle formula. I've just written it in a work equals force times displacement type way. Okay, and so this in total is going to be 4 joules. 4 joules of work done. And then for section number 2, we have 6 newtons of force, but that's the whole time. So there's no divided by 2 going on in this section. So 6 newtons of force times 2 meters as well. It ends up at 4 meters after this whole time, but it wasn't 4 meters in this part number 2. It's just 2 meters. So that equals 12 joules. And so the total work that was done is both of those put together, which is 16 joules. 16 joules of work was done. So that's how a force position graph works. Again, we're not going to use it much, but we are going to see it again, so I wanted you to know what it looks like.